Hello, ladies and gents. Welcome back. We are going to start exploring Chapter 2 today, which is going to be all about chemical components of the cells. And really what it is, it's going to be a little mini chemistry lesson. So we're going to take a look at some of the bonds that atoms utilize to form molecules. And we're also going to take a look at things like macromolecules and what exactly they're composed of, meaning their monomers, as well as the chemical reactions that they utilize when they are building versus when they are being lysed or pulled apart into smaller pieces. So here is the chapter content. As I mentioned to you before, we're going to take a look at chemical bonds. We're also going to take a look at the small molecules in the cells and how these small molecules can then work together to eventually make macromolecules, which are more of a polymer, more of a complex structure. And we're definitely going to see what kind of roles they play within the cell itself. Now, before we actually dive into Chapter 2, I do want to remind you that when it comes time to get ready for your exam, the exam will be solely based on the PowerPoint as well as my lecture. And the reason I want to remind you this when we do Chapter 2 is because I will be introducing some key terms that are not listed in the text, and I've also decided to kind of not be as detailed in certain sections. So just to make sure that everybody's on the same page and understand what needs to be done when it's time to study for your exam, please make sure that you definitely listen to the lecture, take your notes, and anything that comes out of my mouth, as well as anything that's posted on the PowerPoint, that will all be fair game for when I sit down and I write my questions. And obviously, if anything comes up where you have a question, maybe you're a little confused about something, please don't be shy. Reach out to me, send me an email, visit me during our virtual office hours, or as I keep encouraging you to do so, go ahead and post on the discussion board so everybody can kind of get in and provide their feedback. All right, now I know we signed up for molecular and cell biology, but it turns out that all cells have certain chemical as well as physical laws that they have to abide to. And in order to fully understand these laws, we always have to do a little bit of chemistry. So I'm going to try to make it as pain-free as possible and kind of just stick to the main contents and give you like a nice explanation of the different bonds and the molecules that we need to discuss about. But there won't be any chemical formulas on your exam if that's any sort of like relief to any of you. But without further ado, let's go ahead and let's take a look at when we discuss chemical bonds, what are the topics that we're going to be encountering. So here are the chemical bonds. Here's the chemical bonds section, excuse me. We're going to talk about the fact that cells are basically made out of atoms. The fact that the electrons, which can be found on the outermost shell of an atom, is how the atoms can interact with each other to build a larger molecule to form their bonds. And speaking of bonds, we're going to take a look at what the covalent bond is, which basically means that you have atoms that like to share their electrons, and they can share it in one pair or multiple pair. We'll also talk about how they don't have to share equally. One atom can have a stronger pull for the electron than the other. And then also we're going to take a look at how the covalent bonds are strong enough to survive the conditions inside the cell. That was me reading right off the PowerPoint slide for our last sentence. Now, that's not everything that we're going to be exploring because the chemical bonds will take up the majority of the chapter. There are other bonds that we have to kind of chit-chat about. So let's go ahead and click over and see what those are. The opposite of a covalent bond is very kind of like an ionic bond. An ionic bond is formed when electrons don't like to share, but instead what's going to end up happening is one atom will lose electrons, the other one will gain electrons in the process of forming their molecule or their larger entities. We definitely also have to mention hydrogen bonds, which is everything in the name, which indicates that hydrogen atoms are interacting with each other. This is very essential to when we look at the structure of, for instance, DNA, as well as some of our protein structures. We'll talk about how hydrogen bonds are an example of a non-covalent bond that we do see in a lot of our biological molecules because it will help with their overall shape formation. And then at the end of part 1, there's going to be a nice little table, and that table will show us the 4 types of weak interactions that are most commonly seen when we have molecules that interact together. And then we're also going to explore one of my favorite topics, which is pH. So we're going to discuss what makes a solution an acid, what makes it a basic or an alkaline solution, and what makes it neutral, and how it correlates with the pH scale. So there are lots of interesting topics to encounter as we kind of make our way through our little chemistry chapter. So let's get just like a nice little intro as to what it means when you talk about an atom, okay? So when you start looking at cells, what we see happening is at the nitty-gritty, when you just keep zooming in, they're really just composed of atoms. And what an atom is going to be a collection of three things: electrons, protons, and neutrons. Now, each of these will carry its own charge, and what we see happening, and you can obviously refer to the figure that's right here on the PowerPoint, an atom itself will have a nucleus, which is the center part, not a nucleus indicating that it's housing DNA or it's the control center. In this case, the nucleus just literally means that it's the middle part of the atom that you're looking at. And the nucleus itself is going to carry a relatively positive charge within it, and then surrounding the nucleus, you're going to have this cloud. And this cloud is going to be very important because your electrons are going to be orbiting around. And we're not really sure how far the electrons are from the nucleus. So oftentimes when you look at an illustration like this, they're going to just go ahead and draw this larger area that surrounds the nucleus. And usually what they'll do is they'll use different shades of the same color. So in this case, they're using red, and they're using red to indicate the fact that the darker areas of red indicate areas that are more likely to have electrons available in that particular region. Now, your electrons are going to be in orbit, and they will tend to have a negative charge. And then inside of the nucleus itself, what we're going to see happening is that that is where we're going to find our protons. And our protons have a positive charge. And you will also there find your neutrons. Hey, look at me trying to go. All right, neutrons. And your neutrons will have a neutral charge that will go by it. So let's put like a little sign like this, indicating that they have a neutral sign. So definitely know that the protons positive, neutrons neutral. They're housed within the nucleus or the center, whereas the electrons have a negative charge, and they are the ones that will be circulating around in a cloud. So here we go. Here we are looking at figure 2.2, and you can see they're using carbon as an example. They're showing you that within its nucleus in the center section, you have your protons, notice with the positive charge, and then you have your neutrons, no charge over there, and then your electrons here indicated in orbit by the black line. They are going to go ahead and they're going to carry their negative charge. Now, in fact, what we see happening is that when you look, for instance, at your table of elements or your periodic table, oftentimes when you see the particular elements lined up, they're going to go ahead and indicate what we like to call their atomic number and their atomic weight. The atomic number, as you can see right here on the bottom of carbon, is 6. And what that indicates for us is how many protons are housed within the nucleus. So the atomic number is the number of protons. And actually, I don't know why I'm writing it out, because I'm sure it's indicated for us right over here. It says the number of protons in an atom determines its atomic number. The atomic weight is going to be how many protons plus neutrons that particular atom has. So here we go. It says the number of protons and neutrons equal the atomic weight of the atom that we are looking at. Here we go. The atomic weight equals the number of protons plus neutrons. And as you can see from one element to the next, so here's your carbon, here's your hydrogen, that number will vary Okay, but every time you see the mention of an atomic number, please go ahead and indicate that's the number of protons. And anytime you hear the mention of atomic weight, that is going to be the number of protons plus neutrons. Now, while we're on the topic of electrons, protons, and neutrons, I do want to tell you that the number of protons will not change. And that is then why, when you look at your periodic table, that atomic number is nicely printed right on top of the symbol of the element usually, and the number of protons cannot be altered. So that means that on every single periodic table, carbon will have a big old 6 on top of it, and that will always be its atomic number. That will be its number of protons. So we're not altering the number of protons. On the other hand, what we see is that we can change the number of neutrons that an atom has. And when we start doing that, what we do is we start creating these things called isotopes. So if you see a mention of an isotope, that just basically means that we're changing the number of neutrons from one version of the carbon to the other, or one version of the atom to the other. Isotopes will often indicate different characteristics. So for instance, in carbon, some of the isotopes become radioactive and can then be used in medical imaging. Some of the isotopes are used for carbon dating. So it will give a slightly different characteristic to the overall atom. So if you change the number of neutrons, you create isotopes. You can also change the number of electrons, and if you start altering that, then what you're doing is you're creating an ion. Okay? So if you start altering the electrons, like maybe you are giving it away, or maybe you're gaining when you're taking a look at the relationship between one atom to the next, if you see that the number of electrons start to be altered, you're then creating an ion. All right, so just to make sure the number of protons never changes, it's nice and consistent, that is your atomic number. Whereas if you start altering the number of neutrons, you create an isotope. And if you start altering the number of electrons, you create an ion. And last but not least, the atomic weight is the number of protons plus neutrons, which obviously are both housed within the center or the nucleus of an atom. Now, when we start taking a look at all the elements that are out there, we obviously see that you can go ahead and you can compare different organisms and what they're mostly composed of. And I kind of like this graph. This is figure 2.4. And what they did is they showed the difference between the composition of elements within the human body and then within the Earth's crust. And as you can see, it's a completely different variation of elements that come into play. So the blue lines indicate the Earth's crust, and you can see it has really high levels of oxygen and also really high levels of silicon. Whereas if you take a look at the human body, you're going to see 4 elements that will be at the height of it, and those are going to be your hydrogen, your carbon, your oxygen, and your nitrogen. And these are the 4 most commonly found elements within the human body. So your H is for your hydrogen, your C is for your carbon, O is for your oxygen, and N is for your nitrogen. And collectively, they make up about 96% of our overall weight. So they play a huge role in the composition of the body. So now that we've familiarized ourselves with concepts like what an electron is, what a proton is, what a neutron is, where we can find it, how that relates to terms like atomic number, ion, isotope, atomic weight, let's go ahead and kind of take a look at the formation of chemical bonds. Chemical bonds are extremely important because that is how we're going to get the atoms to link together to create larger molecules. So like for instance, if you take a look at water, H2O, that's the interaction of one oxygen molecule with 2 hydrogen molecules. Now, how are these atoms able to interact? Which part of them is interacting, right? And it turns out that is going to be your electrons. So the electrons that are floating around in orbit, they are the ones that will start interacting with one atom to the next, allowing for the formation of a larger entity or a molecule. Now, I want to talk to you a little bit about the electrons because it turns out that they'll be located at different orbitals depending on what energy level they are. So if you don't mind, let's go ahead and take a look at the top corner of the slide on the right-hand side. And I'm going to make myself a little makeshift drawing, so bear with me. So that's my little nucleus. And what I see happening is, as we've seen in previous pictures, we have a little orbital that's going to go around it. And so far, most atoms, depending on the number of electrons, they will fill out more or less orbitals, or I should say energy shell. I'm going to explain it a little bit. But at max, usually you get to about the 4th level. Okay, now the way it's going to work is that electrons love to be paired up. And depending on how many electrons a certain atom has, we'll start filling out the innermost orbital and we'll work our way through to the 2nd, to the 3rd, to the 4th. And once again, it all depends on how many electrons are available. Now, the first orbital, the one that's the closest to the nucleus, this one's going to have the tightest pull on the electrons. This one can only hold 2. So what I'm going to do in green right here is I'm going to draw 2 little green dots, and these are going to be my 2 electrons. And the reason that I'm putting them next to each other is because electrons love to be paired up. If they could possibly be paired up, they want to be paired up. The goal is to pair them up as best as possible and to fill up as many energy shells as possible, because that's going to increase the stability of the atom. So if it has any empty spaces, it's going to seek out interactions with other atoms so it can fill itself up with electrons. And in the same process of stabilizing itself, it also starts building molecules and larger entities. Okay, so the first little orbital, that's going to go ahead and be an energy shell that can only hold 2 electrons. The second one and the third one, they are a little bit of a weaker attraction because they're further away from the nucleus. They are going to actually be able to house 8 electrons. So I'm going to draw my little 8 on the second one and also on the third one. And I'll try to do this really quick because I don't want to waste your time, you just watching me draw little circles, right? Now, one thing I do want to point out is that you're going to hear me say orbital, and then you're going to hear me say energy shell. What's the difference? Well, an orbital is basically maxed out at 2 electrons. So our first little circle, that one that was closest to the nucleus, that one is technically an orbital because it can hold 2 electrons at maximum. Now, if we look at our second and our third circle, what we see happening is that we have more than 2 electrons. So how would you explain that? Well, it turns out that you can have more than 2 electrons. In fact, you can have 8, 4 pairs, because the 4 pairs are at the same energy level. Each pair represents an orbital, and it's almost like you're stacking bracelets together. And by doing so, you're going to create an energy shell. So the whole circle, the whole second circle, I'm going to go switch over to blue so I can draw it for you. This whole circle right here is called an energy shell. It's not called an orbital because an orbital would limit it to 2 electrons. This one is actually called an energy shell that's housing 4 orbitals, because each pair is going to represent its orbital. The same thing can be said about the third circle. This energy shell houses 8 orbitals. Now, our fourth layer, that one is going to have a capacity of 18 electrons. I'm not even going to draw it for you because it's going to take way too long. But it's going to be able to house 18 electrons overall, which means that it can make 9 orbitals. Okay, so when you hear me say orbital, that means you're looking at an area that can only hold a pair or 2 electrons. And if you hear me say an energy shell, that means that one, I'm housing more than 2 electrons. And if you really want to get creative, you can find out the total number of electrons that are being held there. And remember, they like to pair up, and each pair will then form its own orbital. The other one that you might hear, the other term that you might hear is valence shell. Valence shell. The valence shell is the outermost energy shell that you're looking at. And the reason the valence shell is so important is because that's where you're going to potentially find the electrons that are unpaired and are looking to interact with other atoms. What do I mean with that? Let's go back to the chart that's on the left-hand side of the PowerPoint. And what we see happening here is we have a list of different atoms, right? And then notice how they went ahead and they indicated their energy shell. And then they numbered it 1 because the nearest one can hold 2. 2 because that one can hold 8, right? 3 can hold 8 as well. And then 4 can hold 18. And what we see happening here is that they went ahead and they used the color code of red and gray to indicate the electrons. Now, red means that there is an unpaired electron floating around, meaning that that's going to give you the potential of forming a chemical bond with another atom, because remember, our goal is to stabilize the molecules as best as possible, and we're going to do that by pairing up the electrons and filling up whatever energy shell or orbital they're currently looking at. So let me give you an example. Let's take a look at our first element, right? That one is hydrogen. Notice how hydrogen only has 1 electron. So in its first little orbital, it only has 1 electron. That means that it has an empty spot that it's looking to fill up, because it's trying to fill up its orbital so it can be stable as best as possible. And we know that it has 1 empty spot because 1, the electron likes to be paired, and we know that the first energy shell is an orbital, which means it can only hold 2. So every hydrogen atom can go ahead and potentially bind with 1 other atom. It only has 1 empty space. How about if we skip over to carbon? Let's take a look at carbon. Carbon has a full orbital, fantastic, here in gray, but then when we come over to the second energy shell, it has only 4. And remember, its potential is to hold 8. So that means that it has 4 empty spots that it's trying to fill so it can complete its second energy shell and be as stable as possible. So carbon elements have the potential to bind with 4 other atoms. In fact, if we take our carbon and we go ahead and attach 4 hydrogens to it and we create CH4, that's good old-fashioned methane that's formed. Nitrogen, let's go ahead and take a look at nitrogen. In its second energy shell, it has 5 electrons, which means that it has the potential to hold on to 3 more, right? Because our end goal is to get to 8. Oxygen has 6, which means it has the potential to bind to 2 more. So what you could do is you can go ahead and fully explore this chart, and as you can see, as you go down the list, you start looking at the higher energy shells, and you basically can figure out how many empty slots it has for the electrons to pair with. Not all of them will follow that rule. I do want to point that out. For instance, sodium does not follow the rule of trying to find 7 more electrons within the third shell. And I'm going to talk to you more about that in a little bit. But definitely hydrogen, your carbon, your nitrogen, and your oxygen, which remember are the 4 most common elements that you find in the human body, they will follow the rule. So that means that if you're interested in exploring how many bonds I can make, a hydrogen will always make 1 more bond, a carbon 4 more, nitrogen 3, and oxygen 2. Now, I'm hoping that as you're looking at the chart, you're also noticing that helium, neon, and argon are kind of highlighted in yellow. Why is that? Well, it turns out that those are what we call inert gases. Inert gases have a fully filled outer shell. So for instance, for helium, its orbital, its first level is completely filled. For neon, you could see its second layer is completely filled. For argon, its third layer. And because of this, because they have this fully filled outermost shell, a fully filled valence shell, there is no need for them to interact with any other atom. So they are stable by themselves and they will not interact with any other atoms because they have no possibility of filling up empty spots. They just don't have any. So they are stable as they come. Whereas the other ones indicated with red, they do share the possibility of making bonds because they have empty spots on their energy shelf that they're trying to fill because the goal is to become as stable as possible. So here, let's take a look at some illustrations right here. So we can see that we have our two atoms. Let's start on the left-hand side. You have your electrons that are floating up. Notice how it's just one electron on each side. So that means that there's a potential for a bond to be formed because remember, we're trying to pair up the electrons to make them nice and stable. And it turns out that we're basically going to have two options. The first one is that we can form a covalent bond. And in a covalent bond, what we're doing is we're sharing. So if you take a look at the molecule that's being formed, notice how both atoms are interacting with each other and their electrons are being shared amongst the two of them. So we're sharing. The other option would be that you could take a look at the two atoms and maybe one doesn't have an empty spot or a desire to pair up, but it has an unstable or an unpaired electron. So in that case, what it can do is it can take the electron and it can give it away to an atom who's able to receive it. And when it does so, it turns out that the one unpaired electron then goes ahead and is gone from one atom, making the atom more stable, whereas the other atom that's receiving it now has a pair of electrons, which it tends to like. And when we see that happening, when we see that there's not a sharing, but more of a transfer of one electron to the next, we call that making an ionic bond. And this kind of makes sense because remember on our previous slide, we talked about the fact that if you start changing the number of electrons that an atom has, we call it an ion. So in an ionic bond, we're changing the number of electrons that are being carried by two atoms that are interacting with each other. One will lose electrons and the other one will gain electrons. And what we see happening is since electrons carry a negative charge, the atom that gives away the electrons loses some of that negativity and becomes slightly more positive. Whereas the atom that receives that electron now has a higher level of negativity, quote unquote, so it's considered the negative ion. So oftentimes with an ionic bond, you'll see that they'll indicate positive and negative to make it easy for you to identify which element gave away and which one was able to receive the electrons. We're going to explore the world or the differences between covalent and ionic bonds a little bit more because there are lots of little details that I definitely want to tell you, especially when we look at covalent bonds. Not all of them are created equally, but these are definitely the two most common bond types that you would find. So at the core, please know that a covalent bond means that we're sharing, whereas an ionic bond means that one is giving away and the other one is receiving. So you have more of a transfer of electrons between the atoms. Here is a look at our periodic table. I think I should have put this a little bit towards the beginning of the chapter. But either way, I want you to know you will absolutely not need to memorize the periodic table. If there's a piece of information I want you to derive from it, I will definitely be providing you a copy of it on your exam so you can kind of look at it. But I wanted to definitely show you the picture, even though we're not going to memorize anything, because I had mentioned to you that every periodic table will sort of have a number above the symbol of the element, and that number is our atomic number, which remember is the number of protons. So that's nice and consistent. And the periodic table is usually in numerical order. And then also what we see is that there tends to be a number below the symbol, and that is the atomic weight, which is the number of protons and neutrons that you would find clustered together within the nucleus of the element. And usually these elements are sort of like clustered together based on similar characteristics. They can also do different color codes depending on what you're looking for. So in our case, for instance, we talked about the fact that the human body is mostly composed of 4 main elements, and as you can see from the color code, they've been indicated by red. So you can see your hydrogen, your carbon, your nitrogen, and your oxygen being highlighted as clusters of being the most common elements within the human body. Alrighty, so let's kind of go back a little bit to our covalent bonds. So covalent bonds, as I was mentioning to you before, is all about sharing electrons. The illustration that you see on your left-hand side, you can see two hydrogen atoms towards the top. Remember, hydrogen atoms each have one empty spot, so we can get them to interact with each other. But it will all depend on the distance that this attraction is occurring from. So as you can see, if the electrons are too close together, they will repel each other. If they're too far apart, there's no attraction. So they just need to have that right distance so that they can have the sharing of the bonds. Now, that distance will often be reflected in the overall shape of the molecule. So what we see happening is, if you've ever had a chemistry class where you had to use like ball and stick models to kind of model different molecules together, you might have noticed that the degree of interaction between one atom to the next could be kind of slightly different. I guess this would help if I show you an illustration. So my apology. What I'm going to do is I'm going to go ahead and switch over to the next slide, so I can show you the different degrees of how these covalent bonds start to form. So for instance, right here, you can see an oxygen. The circular structure, the ball, represents the element. So this one here is my oxygen molecule. And right here, these little extensions, that indicates the angle at which the covalent bond has to form. And if you compare the drawing for the oxygen, the nitrogen, and the carbon, you see that the spatial arrangements between the bonds will vary from one to the other. It's all about maximizing the attraction between the electrons that they're trying to recruit over. So here you could see that if I take my oxygen and I get it to bind with my two hydrogens, I create my little water molecule. And it's about 120 degrees of an angle that the two bonds make from each other. And it turns out that that is just that perfect attraction form. You can also see in propene, when you have your carbon and your hydrogen interacting with each other, that there is a difference going to be between the length of the bond with the hydrogen in white as when compared to the length of the bond from one carbon to the next. So the spatial arrangement will vary. But at the end of the day, remember, the goal is going to be all about the fact that you are trying to attract the electrons so that you can go ahead and you can do the sharing of the electrons, which is what a covalent bond is all about. You can also have what we call a single bond, which is that you just have an interaction with one single atom within the attraction site, or the bonding site, excuse me. But there's also been cases where you can do things like a double bond or a triple bond. So let's go ahead and take a look at our next illustration for that. So here we go. So it says basically that when you have a covalent bond, you can have more than one electron pairing between the two atoms. And here we can see our little ethane molecule. We see that our two carbons are interacting with each other, meaning you're doing a single bond, so it's a pair of electrons that are being shared. But also what we see happening is that carbon, with its 4 possible binding sites, we can actually see that it can potentially bind and do what we call a double bond. A double bond, and you can see it here, so here's one bond to the carbon, here's the second one. When you do a double bond, that means that instead of sharing 2 electrons, you're actually sharing 4 electrons altogether. And you can build upon this, right? You can do a triple bond, which means that now you're sharing 2 times 3, which is 6 electrons that are being done. And when you do these multiple bonds, what we see is that you start changing the orientation between the atomic connection, between the electrons connection. Oftentimes double bonds will be a little bit more rigid. You'll have less flexibility within the molecule itself, and by doing so you'll create a whole different characteristics. And that is why on our drawing we could see that if we have a single bond, we're doing our ethane, but if we're doing our double bond, we're doing our ethylene or ethene. So it will give a completely different characteristic to the overall molecule that you are forming. I also want to point out, and this is very important, is that when you do a covalent bond, not all electrons are able to share equally. And part of this is based on this concept of electronegativity. Electronegativity basically takes a look at the willingness of an atom to recruit over an electron. If an atom or an element has a high electronegativity, that basically means that it can freely pull as many electrons as it wants, whereas if it has a low electronegativity, it has a harder time attracting or sharing its electrons. Now, what does that mean? Well, that means that if I'm doing a covalent bond, I have to take a look at the electrons that I'm trying to get. I have to take a look at the molecules. Excuse me one second. If I'm taking a look at a covalent bond, I have to take a look at my elements that I'm trying to interact together, and I have to find out if they are at the same level of electronegativity or if they're at a different level of electronegativity, meaning one is stronger than the other. So let me give you an example. Let's go ahead and take a look at our water molecule, right? So here's my little water. It's composed of oxygen and my two hydrogen molecules. Now, it turns out that oxygen has a much stronger electronegativity than your hydrogens. So what does that mean? That means that if I get my oxygen to covalently bond with my hydrogen, they're going to share electrons, but they're not going to share it equally. In fact, the oxygen is going to hoard more of the electrons than the hydrogens because it has a higher electronegativity pull. If we see this happening, usually they're going to go ahead and indicate for you a little partial negative and partial positive charge. And this is not to be confused with the full positive and negative that we'll see in ionic bonds down the way. This symbol is basically to show you its electronegativity. So how willing it is to attract electrons, or how easy it is to attract electrons over to that particular element. Now notice how your oxygen has been indicated as partially negative because it has a higher electronegativity charge, whereas your hydrogen is partially positive because it has a lower electronegativity. So you have unequal distribution of the electrons between the oxygen and the hydrogens. When this happens, because they're still sharing, it is a covalent bond, but to be more specific, we're going to call it a polar covalent bond. So anytime on your homework or on your pre-chapter reading, or when you're doing the questions in the back of the book, if you see them talking about a polar bond, a polar covalent bond, that means that you have a relationship where one element has a higher electronegativity than the other, okay? So a polar covalent bond means that one is stronger than the other. So one is going to be partially negative, the other one's going to be partially positive. One's going to have more electrons versus the other when it comes to the sharing. Now, there's obviously also a case to be made for elements that are relatively close on the electronegativity scale. So electrons, like for instance carbon and hydrogen, they're actually relatively closer on the electronegativity scale. So when you have them form covalent bond, there's a closer of an equal sharing of the electrons between the two of them. If you see that there's an equal sharing, then we call that a nonpolar covalent bond. Now, a nonpolar covalent bond can be found in two scenarios. The first scenario is that you're looking at different elements that are relatively close to each other on the electronegativity scale. That's the first scenario. So they just happen to have the same type of attraction for electrons. The second scenario is what we see illustrated right here, is that you get the same element to interact with itself. So here we're making O2, right? Because we're getting the oxygen to double bond to itself. This is actually breathable oxygen. That's what you inhale. Now, when you see this happening, this is an example of a diatomic bond. A diatomic bond means that both of the elements are the same. So whenever you see that the element is binding to itself, we're creating a little diatomic bond. And a diatomic bond, because everything is the same, that means there's relatively equal sharing, which means it's an example of a nonpolar covalent bond. All right, so just to wrap it up, covalent bonds means that we're sharing our electrons, but we don't have to share equally. If we see that one is stronger than the other, we call it a polar covalent bond. If we see that both of them are the same or they're sharing equally, we call it a nonpolar covalent bond. Now, some of you, when you were reading or studying water, H2O, you came across the fact that it was a polar molecule. So now hopefully you know why it's polar. It's polar because the oxygen has a stronger pull over the electrons than the hydrogen element. All right, now let's go ahead and introduce the other version of the bonds. So covalent is sharing, and then an ionic bond basically says I'm not going to share. Instead, I'm either going to gain or I'm going to lose electrons. So we're going to be transferring electrons. Now, why would you want to do an ionic bond? Well, there's many reasons for it, but usually when you do an ionic bond, that means that you're looking at an element that might have an unpaired electron, but doesn't have an empty spot to accommodate a second one. So when it comes across an element it wants to interact with, it's not able to share because it doesn't have any empty spots to do so. And a really good example of that can be found in sodium chloride, which is good old-fashioned table salt, NaCl. All right, so let's take a look at our illustration on the left-hand side. And what we're going to see is when we look over at our sodium, we're going to notice that when we go over to its third electron shell, which is its valence shell, its outermost shell, it has one electron floating around. Notice how there is no little dotted space to indicate that there's an empty spot to accommodate the pairing of this electron. We're trying to pair it because we're trying to stabilize it as best as possible, but there simply isn't a way to accommodate a second electron. On the other hand, if we go over to chloride, we see that within its third shell, within its valence shell, it has one unpaired electron and it has an empty spot to accommodate a second one. So in this case, if we want the sodium and the chloride to interact together, they can't share orbitals because one doesn't have an empty spot. Instead, what we see happening is that the sodium is going to be donating its electron, its unpaired electron, to the chloride that does have an empty spot to do so. And because you have this donation occurring, this transfer occurring, it therefore is an ionic bond. And at the end of the day, what we see happening is that our sodium molecule becomes more stable because it gets rid of that unpaired electron. Notice how its two energy shells that are left are fully paired up. Also notice how it became more positive. See how they indicated that little positive sign? And that's because it got rid of that one electron, and electrons carry a negative charge. So it became less negative and more positive. The chloride also benefits from this transaction because, as you can see, its valence shell, its outermost shell, is now fully paired up, nice and stable. And as we can see, because it's able to house another electron, it became more negative. So it became, as you can see right here, the little negative sign indicated. You can use that as a really good indicator because most books, when they'll write down chemical reactions, they will use that little positive and negative sign to indicate the molecule that's being formed. And you can then conclude from that that you're looking at an ionic bond. And you can also conclude from the fact that the one that's indicated as positive is the one that donated or gave away its electron, thereby becoming less negative, more positive, whereas the negative sign indicates the element that was able to receive the electron, thereby increasing its negativity. The bottom illustrations, B and C, are just kind of showing you the product of the reaction. So they're showing you like the little crystals that form when the sodium and chloride interact. and they're basically very closely packed together. And you can also see there's a little color photograph of the crystals of table salt, just to kind of give it a look at it. Now, what's going to end up happening is if you take your salt and you put it in water, we see that the hydrogen bonds of the water will start tugging at the sodium and the chloride, and they'll slowly start pulling them apart. And that is then why you create a salty solution, because the salt will start to interact with the H2O molecules of water. All right, and speaking of hydrogen bonds, this is the third bond we kind of have to talk about. Hydrogen bonds you're going to see all over the place, especially when we start exploring the inner mechanisms of cells and their different metabolic reactions, as well as just overall the shape of structures that we're looking at. So here we have two water molecules. As you can see right here, these are my two little polar covalent bonds, right? Because the oxygen is stronger, better at sharing, better at taking the electrons than the hydrogen. And what we see happening is that the two water molecules can interact with each other because the hydrogen is able to hydrogen bond between one atom to the next. And in fact, hydrogen bonds are extremely important. What we see happening is that, for instance, in water, the size and the orientation of the hydrogen bond will be able to determine if we're looking at water in a gas state, a liquid state, or a solid state. In fact, what we see happening is that the most stable form of water is when it's frozen or when it's solid, and that's because the hydrogen bonds are able to space out in their most stable formation, allowing a solid surface to be generated. As you then transition from solid to liquid to gas, we see that the hydrogen bonds are, for instance, responding to thermal changes, like, for instance, exposure to high degrees of temperature. And by doing so, the bonds will start to weaken and their orientation will slightly change, which means that the interaction between the water molecules will start becoming more distant. And as they become more distant, we see that the overall structure then transitions from a solid to a liquid to eventually the least stable, which is going to be the gaseous state. The hydrogen bonds are relatively weaker than a covalent bond, and that's why it's so easy for them to kind of respond to a thermal force. However, don't underestimate them because they still require a large amount of energy from them to transition from one to the other. And that's one of the main reasons why, from a homeostatic purpose, water is such an important regulator of our overall body, like when we look at our pH and our temperature, because even though you have your hydrogen bonds, it still requires a lot of energy for it to cause an overall change within the settings of the pH and the temperature. So they're weaker than covalent, but don't think that they're just so easily to be broken down apart. The bottom part kind of highlights the fact that usually if you have an nitrogen and an oxygen involved with a hydrogen, there'll be some type of hydrogen bond that will come into play, and usually you'll have what we call a donor atom and an acceptor atom. The donor atom is the atom that actually has the hydrogen that will be reaching out to the secondary atom, and obviously the acceptor atom is the one that can then go ahead and start interacting with the charges or the bond with the hydrogen molecule itself. So if you take a look at your bottom part, part B of the illustration, you can see that the structure that was originally bonded to the hydrogen, these are all our donors. And then here, indicated by the red lines, these are the hydrogen bonds that are then interacting with the acceptor atom. All right, so this is the table that I said to you that we're going to encounter towards the end of part one. This basically takes a look at the 4 most common bonds that you will find within biological structures. And we have discussed the fact that you have your covalent bond, which means that you are sharing your electrons, whether you're doing that equally in a nonpolar covalent bond or unequally in a polar covalent bond. You also have an ionic bond, which is non-covalent because we're not sharing, but instead you're transferring electrons from one side to the next. You have your hydrogen bonds, which means that you're looking at a bond between the interaction of at least one hydrogen molecule. That's also an example of a non-covalent because it's a different type. And then there's another one. The fourth one we didn't really discuss. This one is also a non-covalent bond. It's called a van der Waals attraction. This one is usually a relatively weak, short range, more of an electrostatic attractive force, and usually involves the interaction between uncharged molecules. We're really not going to go into van der Waals attraction, but if you want to read more about it, the book does have a nice little paragraph on it. So if you want to learn more about it, by all means, go ahead and take a look at it. And then obviously, if you have questions or concerns about it, reach out to me. I'll be more than happy to chit-chat about it as well. As for the chart, I just wanted to highlight the four most common bond types. Please don't worry about memorizing the strength of the bond or the length of the bond. You just want to be able to give me a nice definition, and like we were chit-chatting about all their different variations, obviously with a heavy emphasis on the first three, since I didn't really mention the fourth one with its short-range bonds of electrostatic forces. So don't worry about the van der Waals attraction. Just make sure that you can tell me what a covalent bond is, that you can tell me the difference between polar and nonpolar, and then definitely an ionic bond and a hydrogen bond. I think this is a nice part to kind of stop for chapter 2, and then the next time we will speak, or I will speak and you will listen, will be when we do part 2. Part 2 is going to take a look at pH, and then we're going to go right into the relationship between monomers, building blocks, and macromolecules, which are going to be our larger entities, things like our carbohydrates, protein, lipids, and nucleic acids. Alrighty, I will, I guess, talk to you soon. Bye.